Okay, we are continuing at electric potential. Okay, we did some of this last time, well, whatever that was. Okay, now electric potential, and then big thing, we did the line integral and all that. But just like the energy was the negative sign, F dot ds, and that negative sign only exists to make this higher potential energy positive. You know what I'm saying? Because if you do work, you lose potential energy and you gain work. So if you calculate work, it has to be opposite. Okay. Now, then this was a big derivation, right? And we arrived at this conclusion, right? Electric potential, we are just taking out the charge, because when you say the work F, right, that's KQ, whatever the test charge that you're introducing to compute the work comes into play. So in case of gravitational potential energy, instead of mgh, you want to just say gh, and that's the potential instead of potential energy. Likewise here, so that this electric potential is potential energy divided by your test charge Q. Okay, so you just integrate electric field dot ds as a dot product line integral. We briefly talked about it, and I'm going to simplify that today. And this is the expression we got last time. And then potentials do add, but this is a big thing that we need to emphasize again. Okay. So that when you integrate E dot ds opposite, you get potential. And then also if you take a derivative, and this is known as a gradient vector, and then opposite of that is your electric field. Okay, so this minus sign means from higher potential to lower potential is the direction of the field. Okay, skip through, then I'm gonna re-emphasize that here. So remember the potential, if you have E dot ds, this is a dot product, that's a key, on curve C, and then opposite of that, that gives you the difference of the potential, delta V. Good. And then likewise, so if you want to calculate electric field from the potential, that is the gradient vector of V. And V is a function of X, Y, and Z. Okay, so this thing, it looks scary because it looks like this. Negative of derivative with respect of V with respect to X, and then I vector plus derivative of this with respect to Y, J vector, it's multivariable calculus, and derivative of this V, same V, with respect to Z, and then J vector, U, right? But you're going to learn this next year when you have this is known as the divergence. Well, no, divergence of it, no, it's gradient. If you, for our purpose, a point charge distributing outside or symmetrical, it pretty much turns out to be regular derivative, radial direction. And now, if you think about it, why wouldn't it be? Because if you have a point charge and electric field going out in all direction, right? And if you move sideways, there should not be any difference in potential. You know what I'm saying? So only thing that matters is if you go that way or if you come in towards the center of that charge. So that derivative actually is a lot simpler than we think. Yes?
So you put
yeah, that's my usual screw up. So this is K vector. Okay? So far so good? Okay, that's the thing. Now, before we do this, I'm going to do a simple calculation. Let's calculate here's a point charge, let's say. Q, positive Q, right? And we want to calculate the electric field at point P. And that point P, the distance from here to here is, what do you want to call it? X, I mean, whatever. Meaning R is equal to 0 here, R is equal to X here, and R is equal to X here. R is equal to, what is wrong with me? That's point P. r is equal to x here. You know what I'm saying? So it's like your variable is the radius r. Maybe I should not use x because most students who are watching this video will say x is a variable. This is really multivariable calculus. You have many different variables. Do you know what I'm saying? You want me to use r or the other way? X is equal to 0, x is equal to r. Should we do it that way then? No, let's do it this. I think because of the next example, remember this thingy we did? Yeah, that was x, so that's what my motivation. If you say potential, what does that mean? Compared to what? Potential means, or potential energy is a relative energy. It's compared to some zero. So where is my potential energy or potential equal to 0 is the question. What is a good reference point? It is at infinity. Because if you think about it, electric field at this point, right here, will be K, the magnitude of the electric field, will be KQ over R squared, correct? And then over here, it will be 0, wouldn't it? Because R is approaching infinity. So that's our 0, which means we have to take the line integral from all the way from infinity away to that direction. So that is the calculation of it. So when we say potential at some point instead of potential difference delta V, we are always referencing from infinity. Okay? And then this makes sense if the charge is negative, then this is negative and it's 0, so we have negative potential. So we go back to this idea of positive and negative potential. You get it? Positive and negative potential. Potential difference compared to infinity away. Okay. And this turns out to be a lot more confusing than it has to. So I'm going to simplify this for you. So this calculation, let's just say, pick a color. I'll go with green. Your potential really means potential at x minus potential at infinity. And hopefully this is 0. You know what I'm saying? Okay. And that should be negative of this and then E dot ds. Good? Okay. Now, first thing is the dot product. What's the angle between the dot product? See, electric field goes out this way. And then our movement, our little ds is tiny bit this way, isn't it? So this dot product gives you, see, cosine theta gives you -1 right there, doesn't it? So what we have for now is this becomes positive and then E magnitude ds magnitude. So far so good? Oh, by the way, this was from infinity to x, correct? Say yes. Okay, now here's another, oh, we can just integrate. No, 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 no. R is our variable, not s. We have to really parameterize this. But if you, I can just throw a little tiny bit dr. And dr is that way now, isn't it? So do you see that ds is equal to opposite of dr? They move in opposite direction. So this goes back to negative now. Now I can change this to dr. You know what I'm saying? Okay, and I'm going to teach you a trick, because this is like triple negative sign, and that's very confusing. We'll calculate it, then I will show you the shortcut. Okay, so this is infinity to x, and then k q over r squared. Let's write it like that. Good. And then this is downhill from here, so negative. And then this is r to the -1 power, therefore -1. I totally forgot k and q. And then from infinity to x. With me? Say yes. So we use plumbing professor. So we have negative KQ. And then this, which one do you want me to write first, x or infinity? Infinity, okay, so negative 1 over infinity plus now 1 over x. No, infinity, positive, and minus using plumbing professor. Good. And then this is 0, so we have KQ over x is the answer we want. Yes? Unless you're taking calculus BCAP exam or that class, yes, you can. Because this is in physics textbook all the time. I mean, in engineers and physicists do this all the time, and I'm pretty sure they accept it in AP exam. Ask your teacher about it, but I think they do. Because it shows up on textbook like this. So much easier than limit and then, yeah, proper integral. Okay, so how are we supposed to take this? This is confusing, right? So the way I like to think is this. Remember, as you do the work, then you lose energy, right? So I would just calculate the work done by the field. The way I like to think is this direction. So if you have a test charge at this point, then electric field, positive test charge, will be pushed to the infinity. Correct? That's this integral, and that's what we have over here, isn't it? And that will give us opposite, negative KQ. This will give us negative KQ over X. Do you see that? Because we are not putting this negative sign and this thingy away. This thingy will give us this thingy, right? Do you see that or not? This integral right here is opposite of this integral. So these two are the same thing. That will give us this answer. Okay, I'm going to write it down. This integral will give us x to infinity of kq over r squared dr. Now we're back here. You know what I'm saying? And that will give us kq and then negative 1 over r. Good. Let's use kq and then 1 over x minus 1 over infinity is what we get. This is so much easier thinking. So far so good? So the way I like to think is I calculate the work done by the field from this position to the infinity, right? So this is where the potential is 0. So in order to store that potential energy, you have to do exact same amount of work from there to here. You know what I'm saying? And then just, it's an easier integral to just set up and think because we are starting right here anyway. So that's how I think. Work done by the field as opposed to you doing the work against the field. Okay, they have to be the same amount. That's what potential energy, or in this case, potential is. Good. Textbooks always have it this way, so by the way, so I'm just letting you used to it. Okay then, we have this problem. We have to calculate the electric potential at x distance, and I'm recycling this picture from your previous work calculating electric field. And then the electric field that we calculated from this example is right here. This is the electric field that we calculated. I mean, it was an ugly expression, right? Okay, there are two ways to do this. Number one is now potential is just kq over some distance, isn't it? So we're going to use that fact. We'll take a tiny ring of charge, and then charge density here is given by sigma, right? And sigma is the total charge divided by the area. which is total charge divided by pi capital R squared. Capital R being the radius of that disk. Good. Okay, then. So this ring charges dq. Okay. Now what we have is space. I'm going to calculate dV. And dV is k q dq over the distance square, correct? Now distance from here to here happens to be square root of this much is r, right? Lowercase r is our variable that varies from 0 to capital R. So r squared plus x squared. X is the constant, the distance away from the center of this axis on the disk. Good. So we have square root of r squared plus x squared. So far so good. Now I have to calculate what dq is. So I'm going to do that here. dq, of course, is area of this ring times the density, isn't it? My pen is not working. Density times dA. You with me? dA being the area of this ring. And that happens to be circumference, chapter 7 idea in calculus class. 2 pi r dr times sigma. Let me put sigma in between right there. Good. Are you with me? Okay. So we have 2 pi sigma k r dr over square root of r squared plus x squared. Eh? That's my dv. And let us integrate. So my v has to be integral from 0 to r of this whole thing. 2 pi sigma k, and then let's write this way so it's easier to integrate. -1/2 power, and then r dr. Do you see u sub coming? So my u has to be r squared plus x squared, and du has to be, now let's not get confused, we're integrating with respect to r, not x. So this is 2r dr. Eh? Substitute it back in, so have, do you see that r dr is du? How convenient, eh? So I'm going to put pi sigma k, and then this is u to the -1/2 power du. Good. And limits of integration, once you have r is equal to 0, u is equal to x squared, and r is equal to capital R, u is equal to capital R squared plus x squared. So far, so good. Integrate. So we have pi sigma k, and then this is u to the 1/2 power. Therefore, we put 2 here. Or we can put 2 inside, but I've taken it outside. And that varies from x squared to r squared plus x squared. Eh? Say yes. Substitute. So now we have finally 2 pi sigma k, and then square root of r squared plus x squared minus x squared square root, so x is the final expression of the potential of the circular disk. Good. Now if you want to, you can substitute sigma value here. But then, let's just leave it because most books have it in terms of sigma anyway. Now, but then there's another way of calculating this thingy. And that's exactly what I did up here. This idea. Instead of point charge here, we are going to place that disk here and do exactly the same thing. Okay, so now say we have a disk like this, and then we are going to put axis at the center all the way to infinity, and this point right here is when r is equal to x, and then this is infinity. Good. And then we are going to need this expression of electric field that we calculated. I think I'm going to have to go get it. I'll just write it down here. Okay, so electric field magnitude happens to be 2 pi k sigma by sigma k. And then, what was it? 1 minus x over square root of x squared plus r squared, like that, from last time, just to make sure, right? 2 pi k sigma 1 minus x, yeah. So that's the correct expression. Good. Now we can integrate this from infinity to here. Okay, let's do this. So first of all, so your v, meaning delta v, v at x minus v at infinity is what that means. The potential is always in terms of potential difference, but then we are referencing at infinity where this v is equal to 0 there. And this v right here at this point, my pen is not, hopefully is this expression that we just calculated. But we are calculating in two different ways. Because we had an easier electric field, but now will it work within the electric field looking like this? Okay? Okay, so this, of course, is from infinity, negative, right? Infinity to x, and then E dot ds. Here we go again. This is why I wanted to make sure that you understand this E dot ds. How many negative signs are here? There are 3 of them. Let's run through this again one more time. The dot product, right? The field goes out this direction, and then ds moves in this direction, right? So the dot product is -1. So this thing becomes infinity to x of E ds. Good. However, my dr wants to go this direction. So we have ds being opposite of dr. So this goes back to negative. So far, oh shoot. I have to use the x here because this is x, not r. R, we can use r because we did r before. So far so good. So this is triple negative sign that still turns out to be negative, and there's a lot of complicated stuff went in here. Okay, I'm gonna substitute that thing in, but I'm gonna take a little unusual approach and actually make it a proper integral. There's a reason, you will see. And this, I want it to be a to x, negative sign here, and then our electric field is, wait it, 2 pi k sigma, and that ugly expression. 1 minus x squared plus r squared. No, we cannot use r, we have to use x because this is a function of x. You get it? You see, we cannot use dr because this is function of x. You get it? Our electric field is in terms of distance x. So let's change this. This is not really greatest mathematical notation, but you know what I'm saying? So this is dx. Okay. Hopefully you're not as confused as I'm worrying about. I forgot x. Let's put it here. You with me? I forgot a lot of things. Negative 1/2 power x dx. How about that? Good. Do you want to be anal and change that to x sub p? If you will, that's the position p, x value. I mean, we are being anal here, so might as well. Okay, let's just put that subscript everywhere. So this is proper integral. Like, why are we doing proper integral all of a sudden, right? There's a big reason, but are you comfortable with the setup now? Okay, now I'm going to integrate. So negative limit a approaching infinity of 2 pi k sigma, and this becomes x. Ooh, u sub again. Can we do our u sub in our head? Watch this. You just write down what you think you're going to get, which is this, and we take a derivative and tweak it backward. So if we take a derivative, this 1/2 power, so 1/2 goes in front, this becomes negative 1/2. Chain rule gives you 2x, and that 1/2 and 2 cancels. So it's just this. Do you agree? That's a clever trick now, isn't it? You want to see that again? Ne? Are we good? Do you quickly take a derivative of this and see if you get that? 1/2 goes to the front, negative 1/2. Chain rule gives you 2x, which cancels 1/2 in the front. You get it? Okay, good. Now we substitute. So we have negative limit of a approaching infinity of 2 pi k sigma, and this becomes xp, right? Minus, and this becomes xp squared plus r squared to the 1/2 power, minus, now this is the confusing part, minus a minus a squared plus r squared to the 1/2 power, like that, eh? So far, so good. Now we take the limit. Well, this one does not have any limit in it. So with this negative sign distributed, we're going to get 2 pi k. And then this thing is square root of xp squared plus r squared minus xp. So far, so good. What is this? This is infinity minus infinity, isn't it? Do you see L'Hopital's rule coming? My point is, if I just substitute the infinity, this turns out to be the same kind of infinity, so that gives you 0. But I thought I would justify that here. Okay? And remember, this expression right here is exactly the same thing as what we got here, isn't it? So this better turn out to be 0, right? Question? So we're going to do that on the side. So let's take a limit here, a approaching infinity of a minus a squared plus r squared to the 1/2 power. Okay. This is a square root, huh? What would be a clever trick? I guess, really? This is turning out to be a little more difficult than I wanted to. I don't want to do power series expansion that you haven't learned yet. But it is what it is. This thingy turns out to be A plus 1/2 A. I'm scaring you, right? Yeah. Let's not do it. Okay, eventually you will learn about Taylor series expansion, but this turns out to be same type of infinity. You can kind of see, right? If A gets really big compared to R, then this is insignificant, so A squared square root. You know what I'm saying? Yes. Yes. That's what I was hoping, but this is minus sign, so we cannot really take. Oh, you show the growth rate? The like same kind of infinity. I mean, it's not a proof, but what she's suggesting is this. If you just do A squared plus R squared to the 1/2 power over A, and then show this is at least same type of infinity. Yeah, and this is just as good until you learn Taylor series, which you haven't. That's coming up in a couple of weeks. Okay, so we L'Hopitalise it, so derivative, so that's in, and then this is 1/2, and then A squared plus R squared to the negative 1/2, and then to A, so this 2 cancels that, 2 over 1. Now we can just take the limit, right? A approaches, no we can't, because this thing continues. Dang it, it's the same thing. It'll just go on forever. A over right. Oh, I have a clever trick. This, if you keep taking L'Hopital, this will be the same thing, right? So forget it. Actually, I just remember this trick. This is a nice trick. So you don't always use L'Hopital's rule. Yeah, sorry about that. Let me rewrite this so that you can understand this better. Right? Watch this trick. And then this thingy is 1. You get it? Right, that's better idea. Anyway, the whole idea is this thing turns out to be the same number if you take a limit towards the infinity, so they cancel and gives you 0, which is exactly the same thing. Good? Now, before we do this, yeah, we want to do this. Gauss's law, last time, we calculated the electric field using Gauss's law at some point away from any shape of charge, right? But this could be a conductor or non-conductor. But uniform charge distribution if it's non-conductor. And if it's conductor, charge only resides on the surface. We'd like to visit that idea, why that's the case. Have you heard the idea that if you get struck by a lightning, but if you happen to be in a metal container, then you're not going to get electrocuted? You might fry, but you're not going to get electrocuted. Conductor will prevent any electric field. Okay, so let's look at that idea. Okay. And this also applies to gravitational field. If you dig inside the Earth, of course, Earth does not have uniform density, but assuming it does, then do you feel lighter or do you feel heavier? Do you feel the same? And if you happen to be standing right here at the center of the Earth, you should feel 0 gravity, right? After all, because every part of the Earth is pulling you equally from all directions, assuming you can withstand the heat, right? So that's the idea. Same principle applies here, okay? So we'll figure out the electric field inside and outside of this thing, okay? And then we'll figure out the potential afterwards, okay? So first, outside. So we say R, part A, R is greater than A. Okay? So we put the Gaussian surface out here. And that happens to be R. Good? Okay, then we set up this thing E. Do you still remember this? We called it dA, right? Instead of ds. And that's total charge inside over epsilon naught, right? And then, remember, let me remind you, this was just 4 pi k. Okay, now electric field is perpendicular to the Gaussian surface, and it's the exact same distance, so it has to be constant. So this thing now becomes E, as a review, that, and we'll put 4 pi k q. Q is the total charge inside this uniform distribution. Okay? And then this turns out to be the surface area of our Gaussian sphere, which is my pen, 4 pi r squared, eh? Good. Dividing both sides by 4 pi r squared. This thing is capital Q, so I'm going to change to capital Q. So we have electric field strength happens to be kq over r squared, which tells you that this thing behaves exactly like a point charge at the center. And that's not surprising because the electric field goes out in uniform direction. Good? Okay. Let's consider part B. And part B is R is inside. Okay. So now we put our Gaussian sphere somewhere here. And that happens to be R. Good? Okay, now we set up exactly the same thing. So E dot dA is, now we have to write lowercase q, because this q meaning q inside. You get it? Inside our Gaussian sphere. Okay? And over epsilon. Okay, so likewise, before this becomes E, and this becomes 4 pi r squared. Good. Just recycling our work. The other side, it becomes 4 pi k times q inside. What is our q inside? Whatever it is, it has to be the charge density times the volume of inside, isn't it? And what's our volume then? 4/3 pi r cube is the volume of our Gaussian sphere now, isn't it? You guys see that? This is the volume of Gaussian sphere, Gaussian surface. Good. Which means we have to calculate what rho is. That's the total charge divided by total volume. Oh, our radius of that thing is A, isn't it? Good. Say yes. Okay. Divide both sides by 4 pi r squared. So 4 pi cancels out, r cancels out. So what we have is k rho, and then I'm going to keep this 4 pi, 4/3, and then another pi, and r. Good. Now I'm going to substitute this rho. So what we have is K Q over, can we just do it in our head? Yeah. So we have K Q over A cubed R. Do you agree with that? Because 4 pi cancels, and you have R here and then A cubed in the denominator. Do you see this is a linear function? So amazingly, and you might have heard this before, and this may show up on your mechanics section of your AP exam. If you go inside the planet, assuming this is a uniform density, this function at the center core of the planet, your gravity is 0. Or in our case, electric field is 0. And then this thingy is just linear function until you hit A. See, if R becomes A, then they cancel. I mean A, well, yeah, then you have A squared. You know what I'm saying? So this is exactly same point. And then it stops growing, and this is decaying function now. Right, so this is the picture. So far, so good. Okay, this is non-conductor case. Then what about conductor? Conducting sphere. How does that change? And then I'm going to answer the question, why is electric field 0 inside a conductor? Okay? Suppose there is a charge distribution. Suppose there is some kind of electric field. And suppose here's a more charge, positive charge here, and there's a less positive charge or negative charge, whatever, right? Then it will create electric field going that way, correct? Which means all these positive charges will fly over there, all the negative charges will fly the other way, and they meet and cancel. So see, the thing about the conductor is, it's a conductor. These charges are free to move around inside the conductor. You know what I'm saying? Which means if there is any field, they will move and nullify this field, and field eventually becomes 0. So what ends up happening is, if you charge this with a positive charge Q, all of the charge will be on the surface like this, because they all hate each other and they want to be as far apart from each other. You know what I'm saying? So inside the conductor, the electric field is equal to 0. That's the key. Remember that. So in this simple case, the total charge, all of the charges are on the surface. Good. Now, then, case 1, this radius is still A, so if your R is greater than A, then our Gaussian surface idea looks exactly the same as this example now, isn't it? Because all of the charge inside is Q, so you just get this KQ over R squared. You know what I'm saying? So that's a simple case. Now B, if R is less than A, so something like this, with the radius R, that means what we have is this. K, well, not K, Q, inside over epsilon. But electric field is equal to 0, right? So the whole thing is equal to 0, which means Q is inside is equal to 0. So, you know what I'm saying? So there's no charge inside. Good, good, good. Okay. we're kind of running out of time, so let me do this thingy. So I like to draw the potential graph based on this, okay? So if I have to draw a potential graph, say here, exactly underneath this, so this is V versus R, okay? This is a linear function, and potential is antiderivative of that thingy, right? So do you see that it will go up in some kind of parabolic up to that point? And this point will be KQ over R. You get it? And then after that, it will be asymptotic behavior like this, right? And the field, I mean, potential outside is over R. So you know what I'm saying? Okay, that versus now here. Let's throw the electric field first, the graph. So this is E, my pen, versus R, right? Electric field inside is 0, isn't it? And then after outside, so I guess starts here, right? Electric field here is KQ over R squared here, and then up to here is a 0. So we have this jump discontinuity. Good, 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 good. Say yes. Okay. Now I want you to answer this question. If we draw the potential graph right here, so this is V versus R, what would this graph look like? I'll give you this much. This side is still this, right? What does this side look like? What's the antiderivative of 0? Huh? Just 0? Something that includes 0. It's constant function. Because derivative of constant is 0. You know what I'm saying? So this is what the potential inside the conducting sphere, charged sphere, conducting charged sphere looks like. So inside is constant, whatever this amount is. And then once you go outside, it goes lower as you go far away. How about that?